Dear student, myself Prof. Sukhbir HK. Today we learn new chapter Kinetic Theory of Gases and Radiation. In this chapter we can discuss first part Kinetic Theory of Gases and another one is radiation. These two parts we can discuss one by one. Firstly, we discuss introductory part in this chapter. Can you recall some basic concept in this chapter? First one, what are different state of a matter? Different state of a matter here, different state of a matter. There included three state of a matter. First one is solid state, second one liquid state, and third state is a gas state. Solid, liquid, and gases are different state of a matter. Then we can distinguish between solid, liquid, and gas state. We prepare distinguish between solid, liquid, and gases. First point, due to strong interatomic forces, particles are very close to each other. Due to strong interatomic force, particles are very close to each other. In a liquid, covalent bond between atoms are weak and thus particles are little and away from each other. In a liquid, covalent bond between atoms are weak and thus particles are little away from each other. There is not interatomic force present in a ideal gas. In a gases, there is not interatomic force present in ideal gases. Thus, particles of gases are far apart from each other. Okay. And second point, solid have definite shape and volume. In liquid, liquid do not possess definite shape but has volume, and in gaseous state, gases do not have definite shape as well as volume. And last point, interatomic interatomic spacing in solid is nearly 10 raised to minus 10 meters. In a liquid, interatomic spacing in liquid is nearly equal to 2 into 10 raised to minus 10 meter, and in gases, interatomic spacing in gases nearly equal to 10 raised to minus 9. This is a distinguish between solid, liquid, and gases. Question asked on this topic: how do you distinguish between solid, liquid, and gaseous state? Then we can discuss here. Next point: gaseous law. What is meant by gaseous law? There are three laws. Prepare simple definition of a gaseous law. Law that relate the pressure, volume, and temperature of the gas are known as gas law. Law that related the pressure, volume, and temperature of the gas are known as gas law. There are three basic gas law: Boyle's law, then Charles law, and third one Gay-Lussac law. Gay-Lussac laws. These three laws we can discuss one by one here. First one, Boyle's law. Statement: for fixed mass of a gas, constant temperature, pressure in inversely proportional to the volume. For fixed mass of gas at constant temperature, pressure is inversely proportional to the volume. That is, we can write here V inversely proportional P at constant temperature. This law is called as a Boyle's law. Next one, Charles law. Second gas law is a Charles law. Statement: the volume of a fixed mass of a gas is directly proportional to its absolute temperature if pressure is kept constant, that is V directly proportional to T at constant pressure. Statement repeat here: the volume of a fixed mass of a gas is directly proportional to its absolute temperature if pressure is kept constant, that is we can write V directly proportional to T at constant pressure. And third gas law is a Gay-Lussac's law. Statement: the pressure of fixed mass of a gas is directly proportional to its absolute temperature if volume kept constant. Here we can write in mathematically, that is P directly proportional T at constant pressure. This is called third law of a gas, or third gas law. And next point we can discuss here, absolute zero temperature. What I mean by absolute zero temperature? Definition prepare here: the temperature at which the pressure of a gas would be zero is minus 273.15 degree and is termed as absolute zero temperature. Definition repeat here: the temperature at which the pressure of a gas would be zero is minus 273.15 degree and is termed as absolute zero temperature. Okay, then next definition, Avogadro's number. Definition: Avogadro's number. Definition: the number of particle we consider atom or molecules in a 22.4 liters 22.4 liters of any gas is called as Avogadro's number. Definition repeat here: the number of particle, atom or molecule in a 22.4 liter of any gas is called as a Avogadro's number. Okay, it is approximately taken as this Avogadro's number denoted by n suffix a is equal to n suffix a is equal to 6.023 into 10 raised to 23. This is a value of Avogadro's number. Then next definition we can discuss here, 1 mole. What do you mean by 1 mole? Definition prepare here: 1 mole is that amount of substance which contain exactly 6.022140076 into 10 raised to 23 molecules. 1 mole is that amount of substance which contain exactly 6.022140076 into 10 raised to 23 molecules. This is a definition of a 1 mole. Then we can discuss next point, another point, how is ideal gas different from real gas? Here, how is ideal gas different from real gas? In ideal gas, there are no interatomic forces present, thus particle possess internal energy purely in form of a kinetic energy. On the other hand, the particle of real gases possess both potential as well as kinetic energy. Here particle of real gases possess both energy, that is potential energy as well as kinetic energy. Size of particle is negative in case of ideal gases, whereas the particle of real gases have a finite size. This is another best point in a ideal gas different from the real gas. Here size of particle is negligible in case of ideal gas. Other hand, the particle of real gases have finite size. And third points, ideal gases obeys gas equation, while real gas, instead of obeying ideal gas equation, obeys van der Waals equation. This is a interesting point in a ideal gas different from the real gas. Here ideal gas obeys gas equation, and this real gas obeys van der Waals equation. Here in this way ideal gas different from the real gas. Question asked on this topic: how is ideal gas different from the real gas? And next definition is elastic collision of a particle. What is by elastic collision of a particle? Definition prepare here: collision between particle in which both kinetic energy and momentum of particle are conserved is called as a elastic collision. Definition repeat here: collision between particle in which both kinetic energy and momentum of particle are conserved is called as elastic collision. And next one, ideal gas equation from the gas law. We can derive ideal gas equation from the gas law. We know that there are three gas law. First is the Boyle's law, next one is a Charles law, and third law is a Gay-Lussac's law. We know that we can derive ideal gas equation from the gas law. Here the three gas law apply to fixed mass. Suppose this fixed mass considered as small m of an enclosed gas are first according to Boyle's law. In short, we can write here Boyle's law: V inversely proportional to P at constant temperature. Second, consider here Charles law: V directly proportional to capital T at constant pressure. And next one, Gay-Lussac's law: P directly proportional to T at constant V. Combine these three law, we can write here therefore PV directly proportional to capital T. Then we know that here this above equation we can write here P1 V1 upon T1 is equal to P2 V2 upon T2. In term of number of moles, suppose this number of mole we consider here small n of the gas, we can write here this become PV directly proportional to the NT here. Then remove this proportionality sign, we can write here PV is equal to nRT. Consider equation first. This is a this equation we consider as a ideal gas equation. Here including some term where capital R is a proportionality constant. This proportionality constant called as a universal gas constant, where universal PV is equal to nRT, where capital R considered as a proportionality constant called universal universal gas constant. Universal gas constant, not gravitational constant. Here value of capital R, this become 8.314 joule per mole per Kelvin. Next one, but number of mole, suppose here consider number of mole, here is a small m, small n, then we can write mass of gas, small m upon molar mass, uh, consider as a m0, this become capital N upon n suffix a. Consider equation second here, where n be the number of molecule, m0 be the mass of 1 mole of a gas, n suffix a Avogadro's number. Okay, then the universal gas constant capital R can be expressed in term of Boltzmann constant. This Boltzmann constant consider as a k suffix b here, k suffix b, as capital R is equal to, here universal gas constant we can write here n suffix a k suffix b, R is equal to n suffix a into k suffix b. Consider equation number third, put equation here, put equation 2 and 3 in equation 1, we get here um, equation first PV is equal to nRT, then equation third capital R is equal to n suffix a into k suffix b, then equation first we get here PV is equal to n upon n suffix a into n suffix a into k suffix b into capital T, here n gets cancelled, remaining what, PV is equal to n into k suffix b into T, here k suffix b be the Boltzmann constant. Some question asked on this topic. Using gas law, prove n into k suffix b into T, also state the significance of turn in whole. Then next point is an ideal gas equation is known as equation of a state. An ideal gas equation is known as equation of state. For a gas, a state is specified by a number of physical quantity such as pressure P, temperature consider T, volume V, internal energy capital E, etc. Hence the equation relating this quantity, that is ideal gas equation, known as equation of a state. Question asked on this topic, why does an ideal gas equation is known as equation of a state? Why does an ideal gas equation is known as equation of state? In this way we can complete introductory part in a kinetic theory of gases and radiation. Today we stop here. Thank you.